the topic of the talk is the deformed Dirac operators and scalar curvature. Please, you may begin.
Okay, thank you very much. First of all, I would like to thank the organizers, especially Professor Anton Savin, for the kind invitation. So today, I will talk about some applications of the Dirac operators, or more specifically, some deformations of Dirac operators to the problem on the existence or non-existence of positive scalar curvature on a manifold. So, this is the abstract. So, indeed, the Dirac the origin of Dirac operator goes back to very early. So when Hamilton discovered the quaternion, he wrote explicitly this formula and indicated that it should play a very important role later in mathematics and physics. So it turns out his statement is very correct, because it plays rediscovered and plays an important role in Dirac's discovery of positive electron. And this is the Dirac curvature. And then till the 60s, Atiyah and Singer they defined the Dirac operator on arbitrary smooth and spin manifold. So let's give the definition. So we take a Riemannian spin manifold. By spin manifold, that is a very that it verifies a topological condition such that the second differential class equal to 0. So give it a metric GTM, make it a Riemannian manifold, and then the Levy-Civita connection is denoted by lambda TM, and RTM is the curvature. So then, if we assume that the manifold is even dimension, then with this spin structure and the metric, we can define the bond of spinors. You have a C2 splitting spinor plus S plus and plus S minus is an emission bond, vector bundle, carry canonically induced emission connection. And I will also emission vector bundle with emission connection on the manifold. Then we can define the twisted Dirac operator by the following way. This is Atiyah Singer's definition. The CS small EI is a orthonormal basis, but this operator does not depend on the orthonormal basis. So if we take D plus and D minus, then D plus would map from positive spinor bundle to the negative spinor bundle. Then it is an elliptical operator. So the index can be defined in this way. This is because that the D plus and D minus are formal.
Dear Chan, we have one problem. We don't see your current slide. We only see the slide with Hamilton, Dirac, and Atiyah Singer. So maybe
no.
Now it's okay. Okay. Yeah. Thank you.
Okay. Yes, okay. Do you see this Atiyah Singer index theorem?
Yes. Now we see you all. Yeah. Thank you.
Maybe there's a time difference. Then, so I just repeated these lines are the definition of the Dirac operator. Then the famous Singer index theorem states that the index is equal to the A hat class evaluation of A hat class and the Chern character of the twisted bundle, where this A hat in the Chern wave form. Can you see now the slides of the Chern wave form?
Only Atiyah Singer index theorem we see.
Or maybe we should wait a little. Do you see now the Chern wave?
No, it doesn't change. It didn't change yet.
Really?
Yes, now Likhnirovich. Yeah.
So maybe
Chernbile, yeah, we see. Chernbile, we see.
Yeah, maybe there's a time delay, maybe. So then by this Chern wave form, the index, the topological index can be expressed by this Chern wave form. So then there's the spin condition is important because it has genus of the CP2 is than 0 as C, and also here the early example is the Lichtenau's formula, right, which that the Dirac operator square is equal to the Bochner Laplacian plus the scalar curvature over 4, where the Bochner Laplacian is the negative. So if we assume the scalar curvature is positive, then the Dirac operator the square will be positive, and that means the Dirac operator would be invertible. So the index should be 0. Then combining with the Atiyah single index theorem, you immediately get that if there is a metric of positive scalar curvature on the manifold, then the A genus will equal to 0. And then there is a natural. This is a natural question, important question in geometry, because the scalar curvature is the weakest, in some sense, the weakest invariant of the Riemannian metric. So there's a standard problem. So whether there exists a metric of positive scalar curvature on any manifold, and the digital theorem gives the first abstraction. So can you see the slides now? The next one.
Yeah, Gromov-Lawson we see.
Yeah, okay, great. So for simply connected manifold, and Gromov-Lawson proved that every simply connected non-spin closed manifold of dimension greater or equal to 5 carries a metric of positive scalar curvature. And later, for spin manifold, Stolz proved that if a simply connected spin manifold of dimension larger or equal to 5 carries a metric of positive scalar curvature, if and only if the Atiyah mean single alpha invariant equal to 0. In dimension 4K, the alpha invariant is indeed the genus. So for simply higher dimensional simply connected manifold, the genus gives the precise topological abstraction to the geometrical problem of whether on this simply connected manifold there is a metric of positive scalar curvature. This is a perfect story, but for non-simply connected manifold, there's a lot of difficult problem. So the simplest non-simply connected manifold is a torus. So Xun-Yao and Gromov-Lawson, indeed Xun-Yao first proved in dimension 3. Method applies to dimension less than or equal to 7, and Gromov and Lawson generalized to arbitrary dimension. So they prove that there's no metric of positive scalar curvature on any torus. So Xun-Yao's method is by minimal surface, and Gromov-Lawson is by Dirac operator. So this is exactly what we want to examine. So this here, I would like to see that the deformation of Dirac operator may play a role. So for the simplest case of the deformation, we take a Xi bundle equal to Xi plus and Xi minus. Can you see this slide? And then the Z2 greater bundle. And then Nabla Xi, they take a Z2 greater connection we over a spin manifold. Then we take a V, a self-adjoint odd endomorphism. That means exchange Xi plus and Xi minus. Then the Dirac operator, twisted Dirac operator is formally self-adjoint. But with Z2, with this Z2 splitting twisted bundle, we take the D plus maps to this from the tensor product, Z2 greater tensor product, the S plus tensor Xi plus and plus S minus tensor Xi minus and so on. And for any real T, we consider this deformation dt equal to d Xi plus TV. Then by a standard computation, the square of this deformed Dirac operator would be d squared plus a middle term, bracket term, and plus dt squared, d squared. So now we assume the manifold is complete. The Riemannian metric manifold is complete, and also assume that this endomorphism V is invertible, universally invertible outside the compact subset. And we also assume that the bracket is 0 outside this complex subset. That means V identify two bundles outside this complex set. Then under this one, if this bracket disappears, then the deformed operator square will equal to d squared plus a positive term, which is universally positive outside the complex subset. Then this implies that this kernel of this deformed operator is finite. So we can define the index of this one. And the relative index theorem simply by using the Gromov-Lawson's method. There is a famous paper on complete manifolds, Scalar curvature and complete manifold. Then with this index will be equal to this in the right-hand side, this A term. Then multiply the difference of these two, the same character of these two bundles, those bundles. And this index theorem is indeed the motivation is similar to this original Gromov-Lawson theorem. So the original Gromov-Lawson theorem assumes that the scalar curvature is uniformly positive outside the complex subset. And then the two bundles, psi plus and psi minus, are trivial bundles of this complex subset. So then there's naturally a V identifies these two trivial bundles outside the complex subset. And then since then we can write d squared by using Dirichlet's formula, we equal to Bochner-Laplacian plus scalar curvature. So since now the scalar curvature outside is uniformly positive, so we can let t tend to 0. So let t tend to 0, but the scalar curvature delta 2 is still bounded by delta tilde positive number. So in this case, even we take t equal to 0, the original operator is still elliptic. So we can take the index dt would equal to the difference of these two index with these two different twisted bundles. The right-hand side, the formula is also the same, but the left-hand side is the difference of two index. I think this is the original motivation. They call this a relative index theorem. But they make the assumption that the scalar curvature should be uniformly positive outside the complex set. But if we use this deformed operator V, consider deformed operator, we do not use this assumption of uniformly positivity outside the complex subset. So indeed, one of the early classical application of Gromov-Lawson is they say that they prove that all the so-called area enlargeable manifold does not carry a metric of positive scalar curvature. So what is the area enlargeable manifold by definition? So if we take a closed manifold, for example, and take a metric, take a metric, we call this area enlargeable if for any epsilon, for any positive epsilon, there is a covering space. There is a covering space and epsilon, m set epsilon of the manifold, taking carrying the lifted metric, because the covering space you can lift a metric to a covering space. Then on this covering space, there is a smooth map from this covering space mapping to the standard unit sphere, which is, so the covering space might be non-compact. Even the manifold M is compact, but we assume that this map is constant outside the complex subset. In general, we call this constant out near the infinity. And we assume it is of non-zero degree, and such that for any two forms alpha on the inner sphere, the pullback the pullback is small. The f star pullback is on the covering space is the norm is less than epsilon alpha. So that means if you push forward, the area would be very small. So of course, if M is compact, this definition does not depend, enlargeability does not depend on the metric. Typical example is torus. Is a torus. You can always, if you consider circle, you already enlarge circle and map to a small circle. You can already do this. So this generalized to the torus. And then for any and all also that for any, if you have an enlargeable manifold and then every enlargeable manifold, then you have another closed manifold same dimension, then the connection is also area enlargeable. And then Gromov-Lawson's famous theorem says that if you have a complete spin area enlargeable manifold, and then the scalar curvature cannot have a uniform positive lower bound. That means the infimum of the curvature, scalar curvature, will be less than or equal to 0 if you have a complete spin manifold. The proof is easy. We assume n is even. I consider the mapping in the definition. Then we take a metric on the take a bundle on the unit sphere such that the Zhang character is non-zero, pairing with the sphere is non-zero. This is guaranteed by the Bott generator, and consider the pullback bundle F star E pullback bundle on the covering space, and consider Dirac operator tested by this. Then on the pullback on the covering space, the Dirac operator with this pullback twisted bundle, the square, will equal to Bochner Laplacian plus this scalar curvature. This is equal to the pullback of the scalar curvature, which is if we assume is positive later. Then the formula will be a twisted Clifford action term. But by the area enlargeability, this is Clifford pullback term, curvature term. Clifford term would be very small because this, by definition of current space, you can verify it immediately. So then, if this, we assume this curvature, scalar curvature has positive lower bound, then when epsilon very small, the square would still be positive, positive. So the Dirac operator will be invertible. Then the relative index will be 0. Then by the Gromov-Lawson's relative index theorem, one gets that this index minus the index with the trivial boundary with of the rank of this E, then you get this one. It should be the difference. The relative index should be 0. But the topological application by the Gromov-Lawson says that the relative index topologically is equal to degree f times this some character pairing on S1. But both terms are non-zero. So this contradiction. So the Gromov-Lawson theorem gives the obstruction for the enlargeable manifold. Enlargeable spin manifold cannot have a scalar curvature of uniform lower bound, positive lower bound. Positive lower bound. But on the other hand, so before going on, so let me mention that it's a direct consequence is that on the torus, since torus is area enlargeable manifold, so this gives the proof that torus cannot have any metric of positive scalar curvature. So moreover, since the torus with any connection is still enlargeable, so as a consequence, you can also say that for spin manifold N, then the connection of any spin manifold with the torus of the same dimension cannot have metric of positive scalar curvature. So this when Gromov-Lawson proves this using Dirac operator and Xun-Yao using minimum surface in dimension less than or equal to 3. But later Lecomte have a very nice observation is that the fact that the connection with torus for any manifold to have the property that the connection does not have metric of positive scalar curvature indeed implied that positive mass theorem holds for N. So recall that the positive mass theorem was first proved by Xun-Yao in dimension less than or equal to 5 by using minimal hypersurface method. And Witten first proved positive mass theorem for any closed spin manifold. And Xun-Yao later recently claimed that they can generalize their method to give arbitrary proof for for any dimension, arbitrary manifold. So a long-standing problem is that there's no Dirac operator proof for non-spin manifold for higher dimension for non-spin manifold, even for CP2 connect them with torus. So maybe we have no time to come back this, but anyway, I have some recent result on this, but anyway, then let me start with first state this related relative index theorem. So as I mentioned before, that Gromov-Lawson theorem for complete manifold, they exclude the for error enlargeable manifold that there will be no metric with uniform positive scalar curvature. But we have mentioned that our new index theorem, relative index theorem, using the deformed Dirac operator, does not assume the uniform positivity of scalar curvature near the infinity. So your natural question is that whether one can refine Gromov-Lawson theorem from the uniform positivity to just the positivity on non-compact manifold. Still, there's no general result available, but still that recently we can show that at least for error enlargeable manifold, we can do this. So our result is that for any closed spin error enlargeable manifold, and N is a non-compact spin manifold. So if you do the connect sum, but we still need a spin condition anyway. If you do the connect sum, there will be no complete magic of positive scalar curvature. If you use Gromov-Lawson's method, you can prove easily that there is no metric.
No, we don't see the current slide.
Okay, just I think you still need to wait a few seconds. So can you see now?
No.
Not yet.
No?
Oh.
We see the non-compact.
Okay. Yeah, the non-compact case. Okay, so let me repeat. So we can prove a partial result, not for any enlargeable manifold, but for a very special case is that if you have a closed area enlargeable manifold, so not as a Gromov-Lawson. Gromov-Lawson result applies to any non-compact complete enlargeable manifold. But we assume M is a closed spin enlargeable manifold, and N another manifold is non-compact spin manifold. Then we show that using our new relative index theorem that the connect sum cannot carry a complete metric of positive scalar curvature. So by using Gromov-Lawson's method, you can prove easily that there will be no complete metric of a uniformly positive scalar curvature. But here we just drop this uniform positivity. And as a consequence, that for non-compact spin, any non-compact spin manifold, the connect sum with torus cannot have complete metric of positive scalar curvature. This is also related to the so-called positive mass theorem for non-compact manifold. Indeed, this kind of result are recently interested for those who study positive mass theorem. For example, even for dimension 3, of course, dimension 3, every manifold spin, this corollary is only recently due to lesson Nankai and Yao. And for method for dimension between 3 and 7, it was proved recently by Chadosh and Chao Li. Since they are using minimum surface mass, they do not assume N is spin. But for arbitrary dimension, this is for spin manifold. So this is we just the parallel to Wittenson result in the closed manifold case, and it has been proved that such kind of result are closely related to, as I mentioned, positive mass theorem in non-compact setting. For general manifold, for non-spin case is still open. Is still open. So I think I have only several minutes left, but if time permits, I would like to mention another result, but I'm not sure if it was time enough. Tautologically speaking, I'm not going to detail. So let me just going back to this positive mass theorem page. So in this last line of the previous page, maybe it will show back in a few seconds. I mentioned that no Dirac operator proof for non-spin manifold in general. But recently I can show that for spin C manifold, one can prove by using Dirac operator this positive mass theorem for any dimension. So the main idea is that for spin C manifold, the main obstruction is the codimension 2 submanifold with objects which becomes objection. So this codimension 2 can come from, let me just say, without going to the slides. So we'll see. So the spin C manifold by definition is that there is a complex line bundle, or equivalent is the rank 2 real vector bundle over the manifold such that the C1 class or the Euler class is mod 2 equal to the second steeple-friendly class. So the main point is there is a rank 2 bundle. So you take a transversal section. You take a transversal section of this rank 2 bundle. Then the zero set is the codimension 2 submanifold. And this is the obstruction. This is the obstruction. So outside this rank, this codimension submanifold, the manifold is spin. The manifold is spin. There is Dirac operator. So you can consider the spin C Dirac operator, which the line bundle outside this one is a trivial. Outside is submanifold trivial. So then you can somehow using deformed Dirac operator to localize everything to near this submanifold. Then you do some analysis. So this is our claim that for this we can get at least for proof of Dirac operator proof for spin C manifold case for arbitrary dimension. So that the torus, for example, the torus connected with any spin C manifold will not have metrical curvature. Of course, for any dimension, Shun-Yao claimed they can prove for any manifold by using minimal surface method. But at least for spin C manifold, I think I can do this by Dirac operator also. So in summary, I think Dirac operator or the deformed Dirac operator, as mentioned in the previous talk, that I saw that the deformation by vector field of the Durham-Hodge operator, and also later the symbol on the symbol level paradigm means deformation of the Dirac operator and so on, plays many important roles here. I just want to emphasize, even for the purely geometrical problem on the existence of symmetrical positive scalar curvature, Dirac operator, deformed Dirac operator, also plays an important role. So I will stop here. Thank you very much.
Are there any questions or comments?
In the end of the talk, you mentioned that spin C manifolds, they geometrically correspond to codimension 2 manifolds. And do we expect for general manifolds, is there some kind of abstraction to spin structure or something of geometric origin?
In general, there's abstraction is still codimension 2, but with 2-dimension 2, it's a stretch, just some called a variety. So that means not a smooth manifold with stratum. With CW, you can see the CW 2 codimension 2 CW complex. You can see this, but on this, at least I cannot. So first of all, the singularity, possible singularity cannot be deal, and for the on the other hand, that I worked with spin C Dirac operator. So then on the general, without this lamp bundle, I'm not sure whether one can do this, because I worked on the whole manifold.
Yes.
But the obstruction is that you can tautologically, you can, of course, you can cut out this codimension, cut out the small neighborhood of codimension 2 CW complex and doing Dirac operator on the rest. But then you will meet the difficulty of mean curvature and so on around the possible boundary. But for me, I work on the spin C operator, so on a smooth manifold, try to do globally.
Thank you. Thank you.
Other questions? Let us thank. Thanks a lot. That's all for today.
Okay, thank you.
Thank you very much.
Thanks a lot.
Thank you.
Yeah. Bye-bye.
Bye-bye.